So welcome. So let's talk about the nature of light. We talked about this before last time, so let's just briefly go over it. So we talked about E equals hf. So the energy of a photon is equal to a constant times the frequency. So blue light has more energy than red light, photon for photon. And then we talked about early on, they decided to try and measure the speed of light, and so telescopes came into existence in about 1608, and they saw the moons of Jupiter for the first time, and by 1675 they were using it to measure the speed of light, which is quite impressive. And as I said last time, basically there's this idea that as the Earth, if we look at our diagram, as Earth is approaching Jupiter, Earth moves quickly, Jupiter moves slowly. As Earth is approaching Jupiter, it can measure the interval time for every time Io sneaks behind the Jupiter. So it does it on average every 42.5 hours. And what you measure as you are approaching is you measure a time scale which is less than that. And as you're leaving, as the Earth is leaving 6 months later, you're noticing that the time scales are longer than 42.5. And so what's going on? And what's going on is if I imagine the instance when the moon does go into eclipse, there's always a time delay. And so there's going to be a time for the light to get from here back to here. So there's a time delay, and initially, let's say the Earth is there, I'm exaggerating tremendously here, and let's say when the second eclipse comes in, the Earth is there. So it has a longer distance to travel for the first instance, so there's more of a delay, and it's got less distance for the light to travel for the second one, so we have a shorter delay. I'm only going to draw those two. So this is the long delay, and this is the shorter delay. Because of the distance, that's a long distance, and that's a short distance. And so when you measure this, it's not 42.5, it's less than 42.5. And then over here, if we imagine it going away, well, we have a delay for the first one, and then there's a longer delay for the second one, and so we get a longer than 42.5 hour period for that. And if you measure that and you know the geometry of the solar system, you in principle can measure the speed of light. And he did, and the only problem he had was that because he had the wrong size of the Earth's orbit, he had this diameter he had incorrect. So he got an answer which was not bad. I mean, 2.1 versus 3.0 or whatever. In lab, we'd be very happy about it, you know. But and if he just had the better number, he would have got a better answer. And then we have Fizzo, and Fizzo did it in a very brute force, direct way. He basically shone a light, and he shone it over about, I don't know, two kilometers. So it's a fair distance, but it's just an instant. The light takes next to no time to travel that distance. So it's a timing problem. And he came up with a very innovative thing, which was basically he used tooth wheel. He used gaps in a wheel. The light goes out from one gap and comes back. So I'm going to draw this kind of like I can't move the tooth, so I'll move the light. So the light goes out through that, and it comes back, and the tooth has come down, so it hits there. And the light goes out, and the tooth is going faster, so it hits there. And the light goes out, and the tooth goes really fast, so it comes back through. So the idea is you spin this wheel faster and faster and faster, and you don't see the light returning, and then eventually you see the light returning. And it's because it went out through one tooth and came back through the other tooth. And doing that method, he measured 3.1 times 10 to the 8 meters. I think we did this last time, but let's just do it again briefly. So basically, we have a light source and we have a mirror, and that distance is 1 kilometer. And he has a wheel, and the wheel is spinning at 400 rev per second, and there are 100 teeth, which means 100 gaps. So, okay, so we say that our speed of light equals 2 times the distance, because you've got to go there and back again over the amount of time taken. That would be meters per second, which makes sense. And so our distance is 2,000. We want to work in meters rather than kilometers, so it's going to be 2,000. And now we've got a bit of intuiting to do. If there was just one gap, then it would take 1 over 400 seconds for this thing to spin once. If the revolution is 2 times a second, it's half a second per revolution. If it's 4 times per second, it's quarter of a second per revolution. If it's 100 times a second, it's 1/100th of a second per revolution. And if it's 400 revolutions per second, it's 1/400th. So we know it's 1/400th. Now we've got to take into account the number of teeth. And if you had two gaps, it would be half the time. If you had 4 gaps, it would be a quarter of the time. If you had 8 gaps, it would be the 1/8 of the time. We've got 100 gaps, so it's going to be 1/100th of the time. So it's this times 100. So that comes out to be, the time comes out to be 1 over 4 times 10 to the 4. So this comes out to be 2,000, and that flips times 4 times 10 to the 4, which equals 8 times 10 to the 7 meters per second. And that's, I deliberately made it so it wasn't 3 times 10 to the 8, because, you know, you could just write the answer down, you know. So this is weird light. That's how you do it, okay? You can go online, actually, to Gutenberg, the Gutenberg project, and they basically, it's in memory of the Gutenberg press, and the Gutenberg press was like the iPhone of the 350 years ago. Used to be, you'd communicate by writing letters to people, or maybe you'd write a book by hand, which is why books were very rare and very expensive. And then the press came along, the printing press came along, and suddenly you could knock out 100 copies or something relatively easy. That enabled a whole bunch of different, if you like, technologies. And one of the technologies was, in Britain, some of the scientists of the day recognized the fact that they could communicate with the scientific community by publishing papers and books. And so, rather than a haphazard way where I write to my friends and maybe you're a friend and maybe you're not, and if you think it's good because you're a friend, and you make copies of it and write to your friends. So a very haphazard way of spreading knowledge. The idea is we all join this club called the Royal Society, and because we joined the club, we get a newsletter which has the latest research printed on a printing press, and we all see the same stuff. And we can even go one stage further, actually, to make it so that people actually get value out of it. We'll have quality control standards. So if you're interested in disseminating something, you send it to me, and I pick 3-4 people who I trust, and I say, what do you think of this? And if they say, we think it's good, it goes out. And if they say, we don't think it's good, I go back to you and say, hey, you know, can you make these changes? This is the criticism. And to this day, that's what happens. It's not just the Royal Society now. There's a whole bunch of different journals. But the process from when you send in your paper to when it gets published, if it gets published, in some cases is as long as 18 months. And it's done anonymously. The peer review is done anonymously, so you can't phone up your buddy and say, hey, what are you talking about? You know, you should let my paper through. For the most, I don't know of a case where I've ever known the name of a reviewer. Sometimes I've been able to guess, because you get to know people in the field. And I have the experience of having a paper rejected, and having a paper accepted without any revisions in the same semester. And it's kind of the way it goes. It's kind of like my paper that was rejected was rushed. And yeah, it was like, in a way, they said it was not important enough, which I actually disagreed with. I think it was important. It was worth a short letter. And because I found it hard to do, I wrote it as a long thing. But it was only me that found it hard to do. But I think it would have been quite practical, actually. And then the other thing I did was just this relatively short thing, was just a very nice little experiment. And the reviewer, there were two reviewers, and one of the reviewers said, "This is a nice little paper," which I thought, well, I kind of kept that letter. It was kind of nice. So are the swings and arrows, and if you're around academics, you'll find that sometimes they're depressed, and that's because they got the hard word about one of their papers, and other times they're elated because it got published. But that's the way science works, and you got to be a bit thick-skinned about it, and you got to, you got to recognize the fact that if you have outlandish ideas, you better have a lot of good proof for it, because no one's just going to accept it. It's not a perfect system. I mean, my old supervisor said that he published a paper based on some research a student had done, which is the way it usually works, is an academic faculty member will have students, and they'll publish papers together. It's like the parent and the child, they publish it together. In a way, the academic faculty member shows the student how to do it, and then they're independent as they get on. So he was doing this, and they published a paper, and a few months after the guy graduated, they got another student, and continue this work, it's interesting. And the second student couldn't repeat what the first student had got. That's worrying. Because the way science progresses is, you do something, I read about it, I go, oh. And in making progress, I inevitably repeat what you did and go on. And if I don't, then I write a letter or a paper saying, hey, I did this and it didn't work, basically. And there's a self-correcting thing. So in his own lab, he discovered that something he'd published was irrepeatable. We're using the same equipment. So, and at first he was like, just, go on, do it again, and then finally he ended up going himself and checking it and realizing that the first data cannot have been right. And there's a whole bunch of questions about why was it not right, mistakes or deliberate, there's all these issues. But the key thing is, you correct the records. So they sent a second paper in saying, basically they dress it up nicely. It's almost like they're talking about somebody else, but, we have data that disagrees with the previous paper, and so on and so on. Not saying that's me, by the way, And he said the thing that was kind of frightening was in that period of time, various people had referred to the paper, and it was wrong. And no one had actually gone back and checked it. They just, that's an interesting, so they referred to it. So mistakes can come in. But the idea is they don't last for long, because inevitably somebody does repeat it, and they go, that's not going to work. And it's a competitive system. So if I can, frankly, it's a bit harsh, but if I can prove somebody else is wrong and publish it, that's another feather in my cap, which helps me with my career. I shouldn't be gleeful about it, but it's something to talk about. I want to make this point really clear, because it's kind of like, it comes under attack from time to time. Science is not a group of buddies. They are young competitors. You'll have a few buddies in there. But in the room, there'll be people who kind of want you to, they want what's good for them, and not necessarily what's good for you. And that's okay. That's kind of very, very natural in a way. That's the way animals survive, and we're polite about it, but so this idea that we all sit around a table and somehow concoct something, it's not true. There sometimes are grand old men. As you get older, you realize people defer to you a bit more until you get to a certain age. Then they start brushing past you. It's kind of very interesting. There's this fall-off point where when your hair goes that little bit too white, you kind of like, people go, yeah, yeah, and they start talking, you know, and you go, oh man, I'm over the hill. But, you know, people can maintain a fair amount of power, and they can be influential, and they can hold things back, but they can't stop it, you know. So if you let science do what science does, and you don't rush it, it'll get the right answer in the end, you know. Newton, so Hooke encouraged Newton to take part in this, and Newton did, and he sent a paper in. It was experiment-based. They had this idea about, you know, data-driven research, like we do today. And some old-timers like me basically read it and said, oh, this is nonsense, because we have our ideas of, having never done an experiment, we're still experts because we're high in the field, and criticized it. And rather than basically challenging and saying, well, prove me wrong, he got angry. And he basically did not publish with them again until he had the full story. And so he wrote these books, and they're quite thick books. And what I'm saying is, with the Gutenberg press, you can go online and you can actually get the entire book. He's got one on mechanics and he's got one on light, and they're kind of frightening thing in a way. So he's not right about everything. He has some really wacky ideas in there, but he has an awful lot of solid bedrock in there. And the thing from a teaching point of view that's kind of remarkable is, to this day, we use the same kind of visuals. You'll see this in many textbooks. It's redrawn, but even to using the eye kind of thing, you know? And the same language, and sometimes the same terminology. As we're going to find out, I'm pretty certain, I haven't checked on this, but I think it's pretty certain that Newton basically wrote an equation which was 1 over P plus 1 over Q equals 1 over F. And I hate it because I'm slightly dyslexic. So if he'd written 1 over P plus 1 over Q equals 1 over F, I would have been much happier. And that, I mean, any educator knows you don't use little a and little b, and you don't use little p and little q, because a portion of the population has trouble with those. But because of that, I think we're still using them today. And you think somebody would just change it and go, like, you know. So tremendous influence 350 years later. So Newton's basic idea was, I'm going to publish books, and you can argue with a book, but, you know, I'm going to publish the book. And he did. He became really quite powerful within the community. And he kind of never forgave Hooke. Hooke had been his hero when he was a kid, when he was a young scientist. Hooke was 7 years older than him. So, like, you got this guy, you know, you're in your early 20s, they're in their late 20s. You know, you're not connected, they're connected. It's like, oh man, I want to be like him. And that was where Newton was about Hooke. And then he felt that Hooke had persuaded him to submit a paper to the Royal Society, and then he got insulted. Who do you blame? You blame Hooke. And throughout their lives, there was this, like, real issue. And there's this famous thing where Hooke was writing to Newton, trying to persuade him, look, even though your first experience wasn't that good, please be involved, because we really do respect you, and, you know. And Newton wrote back this letter, and it sounds really nice. It's kind of like, oh, you know, if I see further than other people, it's just because I've stood on the shoulder of giants, you know, like I'm just the next level in line. Newton, by the way, was really tall. And Hooke, by the way, was really short. So was he saying, you know, hey, yeah, I've stood on the shoulder of giants and you're no giant, you know? Or was it just without thinking, you know? But after Hooke died, Newton took over as the leader of the Royal Society, and it basically erased Hooke. It's like, Hooke's got Hooke's law. And yet he was involved in most of this stuff. He was making contributions, but Hooke's got Hooke's law. And, you know, Newton was in charge of the Royal Society, and we used Newton for pretty well everything, you know. And he's right, but, you know, it's kind of like, historically, It was his version of things that we remember. Look it up. It's interesting. You get to look inside somebody's. You can see him hunting for the word sometimes. The word's not been invented yet, and he's trying to describe something. He's not got the word for it, and it really slows him down. So it's kind of interesting. Okay, so let's talk about reflection and refraction. So reflection is light comes in, bounces off. Photon for photon, if you like. In theory, I guess, or in practice, the light is absorbed and another photon is emitted, but, however you want to think about it. It doesn't matter how it happens. What matters is it happens. And if we have a flat, shiny surface, it's like a mirror. And if we have a rough, shiny surface, it's like a satin finish. They're the same material. They're the same reflectivity. It's just this is smooth and the one over here is rough. And so they reflect as much light. It's just that the one on the left keeps the image integrity. It goes 1, 2, 3, 4, and that becomes bounced 1, bounced 2, bounced 3, bounced 4. It's the same spatial separation, whereas if we do 1, 2, 3, 4 coming in, because of the surface, 1 bounces almost back on itself, and 2 ends up way over here, and 3 ends up there, but 4 is going off in this direction. So we lose the integrity of the image. As much light is reflected, we just lose the integrity of the image. And we call the mirror-like one specular, and the diffuse and the rough, the satin finish type one, diffuse. So just know those terms and know what they mean. If we take a mirror, we can do experiments. So what Newton did was he took a pin, and he had his mirror, and then he looked. So let's draw his eye, and he put a third pin. So what happens is this guy appears to be here, and this guy appears to be back here. Yeah, that's what mirrors do. And he kind of lines things up. So he puts a pin there in line with these two, and he puts a pin there in line with these 3. And then he draws lines, and he goes, well, there's my incident ray coming in, and here's my reflected ray coming out. And he finds the angle between the incident ray and the normal to the mirror. And the reflected ray and the normal to the mirror are the same. So he says angle of incidence equals angle of reflection. He actually says a bit more than that, because I could have something coming down from the left at 60 degrees, and it could bounce off towards you at 60 degrees. Still, the angle of incidence equals the angle of reflection, but that's not what light does. If it comes down from the left, it goes off to the right. So we need another thing which we say the incident ray, the reflected ray, and the surface normal are all in the same plane. There's no kink in it. There's no bouncing to one side. So angle of incidence equals angle of reflection. Please notice you measure these angles to the surface normal, not to the plane of the mirror. That's the most common mistake. I give you to the plane of the mirror, and people just use that. If you don't draw a diagram, you'll just draw that. You'll put the wrong angle in and get very little credit for it. So. If I have a transparent material, light passes through it. It does reflect. If you were in a room during the day, you can see outside when you look outside. At night, you will see yourself reflected in that glass. That reflection is there all the time. It's just such a low intensity of light that during the day it's swamped by the light from the outside, so you don't notice it. But it's there all the time. So there's usually reflection to greater or lesser extent from a surface of a transparent material. In fact, from the front and from the back, actually. If you look in a shop window at night, you'll sometimes see your reflection twice, because there's the inner, it might be the thickness of the glass, or it might be 2 panes, but there's an inner one and an outer one. There's an inner one and an outer one. Okay, so there's reflection, but there's also transmission of light. And a weird thing happens with the transmission of light, and that is that if I'm at an angle Let's say I have a fish tank. If I look directly at the fish tank, my fish looks like my fish. It's actually slightly bigger than the fish actually is, but my fish looks like my fish. My fish looks like it's closer to the glass than it actually is as well, but that's okay. But if I go to the corner of the fish tank, I've suddenly got two fish. And after a while, they're dancing in unison. Then you go, oh, it's the same fish. It's like I'm just looking at it from two different perspectives. So there's like a bending of light that's taking place. And this is caused by a kind of phenomenon which is called refraction. Refraction is kind of based on the physical system whereby light slows down in comparison with vacuum when it's in a medium, a transparent medium. So it can travel through a transparent medium, but it travels slower. Don't care why. I mean, I'm not sure I really know why. It just travels slower. Diamond, it travels really slow in. The speed is about 2.5 times slower. Water, it's basically not so great, maybe 1/3 slower. So we can characterize transparent materials by how much they slow the speed of light down, and we call that the refractive index. And it turns out that the bigger the refractive index, the bigger the bending effect on the light. They're both manifestations of the same phenomenon. So we find it useful to characterize materials in terms of their refractive index. And their refractive index is given the little letter n. We're going to use letters over and over again. And it's basically the speed of light in vacuum, which we call c, over the speed of light in a medium, which we're going to call v. And because the speed of light is always slower in the medium, n values are always bigger than 1. Now, I think there's some games that in modern physics they can play where they mess with refractive indices, but there's some. I saw a little article about people claiming to have a speed of light faster than the speed of light, but I think it's suspect, or if not disproven. Yes. I'm sorry. Maybe a couple of years.
Yeah, the core was slightly unplugged, so it's wrong.
So it was wrong? Yeah, okay, good. That reassures me. So you can have a refractive index of greater than 1. So we say, okay, light travels from one medium to another. Its frequency does not change, but its wavelength does change. So if V equals F lambda, which we learned, and V is changing, then either F is changing or lambda is changing or both are changing. We link F with colour, and colour doesn't change. Now, if you look at a piece of glass, sometimes there's a green tint to it, but that's something else. If I have transparent material and light comes through it, that photon does not change its colour. Maybe if I have white light coming through, I let more of the red ones through than I let the blue ones through. That's a different issue. But I can't send through monochromatic light, one colour light, and have it change colour. It's not going to do that. So it's not slowing down because the frequency changes, it's slowing down because the wavelength changes. So we can visualize it like this. And we find it convenient to think about this as matching soldiers. So here's the soldiers making one step, and there's the soldiers making another step, and here's the soldiers making one step, and here's the soldiers making another step. So they're making rapid progress by making big steps. But then when they get in here, they match at the same frequency, the same rate, but because they take smaller steps, they don't go as fast. So that's a visualization that sometimes helps. That ties in with a thing called Huygens principle, who talked about wavelets and the like. We'll get to that. So we can represent our refractive index in terms of speed, but we can also represent our refractive index in terms of wavelengths. If our speed equals f times lambda vac equals c, and f times lambda n is v, then I can just cancel these guys out and I get this guy. So it's the same equation. This is an important equation. We'll come back to that. What it says is that the wavelength in a medium other than vacuum is equal to the wavelength in vacuum over the refractive index. That's a very useful equation, which we're going to deal with later on. So it's a figure of merit, isn't it? It's a dimensionless figure of merit. If we put this stuff in a situation where we got a non-normal approach, so my angle of incidence is now not at 90 degrees, I start seeing a bending effect. I get my reflection, I don't care about that, but I see this transmitted ray, we call it the refracted ray, and the angle between the normal and the refracted ray is not the same as the angle between the incident ray and the normal. There's a bending effect. It's a dogleg effect, if you like. And there's two possibilities. One is that you bend towards the normal, and the other one is that you bend away from the normal. And it depends on the relative refractive indices. So the one I remember is if I have air and I have water, I bend towards the normal. So this is a low refractive index, N1 and N2. If N1 is less than N2, I bend towards the normal. And if it's the other way around, I bend away from the normal. So I can always figure out whether I bend towards the normal or bend away to the normal, because I remember one example, and then I can figure out the changes from that one example. Don't remember all of the examples. Remember one example, and then know if I switch things, I switch things. How much does it bend away from the normal? Or how much does it bend towards the normal? Depends on that. It's given by this angle, Snell's law. By this equation, Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. Sine theta 1 is basically, there's my theta. It says instant here, but of course I'm talking about that bit. This is not a particularly good diagram on my part, I'm sorry. And it's funny how you look at things and you don't notice things, and then you do. So it is the coloured angle. It's not the clear angle, it's the coloured angle. And the sine of that angle basically would be, if there's a velocity in this direction, the sine of that angle is the velocity in that direction, the velocity in that direction. So just learn the equation. Okay. We say refraction is the bending of light ray as it passes from one medium to another. The incident ray, the reflected ray, and the refracted ray and the surface normal are all in the same plane. And this occurs because the speed of light is different in different media, and so we say, oh, okay, N1 sine theta 1 equals N2 sine theta 2. Here's some examples of different values of N. The standout is diamond, 2.419. Really slowing light down. Big refraction effects. And as we'll see in a minute, big dispersion effects. It separates the colours of light a lot. Air basically has no effect. It's like, 10,000th, 100,000th. It's like not significant. Water's constant pretty much. I suspect if you change the salinity, you might change the refractive indices. And crown glass. Crown glass is a type of glass. There's a whole bunch of glasses, from flint glass, crown glass, They have different compositions. They have different crystallinities. Glass is typically amorphous. But they do have crystal glasses, and I'm not sure what the structural difference is, actually, to tell you the truth. But if you go to Waterford and you buy crystal glass, it's very expensive. It's very heavy. It's not like your tumbler that you buy, at your local store. It's like different animal to some extent. So glass covers a whole bunch of different materials. A couple of quick questions. So if you got your clicker, click it. If you don't, it doesn't matter. But in which medium does light travel fastest? So what do you think? Which does it travel fastest? How many people have clickers? Just hold them up so I won't wait for a long time. So about 7 people. So I'll wait for another few seconds or so. There's 7. We'll stop there. And basically, what are people saying? A bit mixed actually. So let's think about this. So what we say is that N is equal to C over V. So the bigger the N, the smaller the V, because C's not changing. Does that make sense? C's constant, so the bigger the N, the smaller the actual velocity in that material. So a big N means a slow speed. So this is slow, and this is fast. So which one does the medium travel fastest? It's going to be water. Okay, cool. Refractive index of material is 2.0. What is the speed of light passing through the material? Do you have got that? So let's have a look at this. We've got 4 responses. Go on, let's get a couple more responses here. Refractive index of material. So we know N, and I want to know the V. I know C is the speed of light, 3 times 10 to the 8. So I should be able to work this out. I'll give you a few more seconds. I'll give you a little bit longer. So write down the equation and then almost there. One more. Come on, number 7. Come on. You can do it. Come on. Yes. Thank you. Let's stop it. Let's go here. Mainly B, a little bit of C. Let's have a look. So we're going to say, well, let's have a look. N is equal to C over V. So V is equal to C over N, which in this case is 3 times 10 to the 8 over 2, which equals 1.5 times 10 to the 8 meters per second. 1.5 times 10 to the 8. Cool. Very good. In which medium does light have the longer wavelength? I'm going to do this one. So N is equal to C over V. Let's have a look. This is F lambda over F lambda. And that's a constant. So the bigger the N, the smaller the V, the smaller the F lambda in the medium. So in which medium does the light have a longer wavelength? If I have a big N, I have a slow, and the way I become slow is I do shorter steps, which equals small lambda. And if I have 1.3 I'm going fast, well it's not as slow, which equals longer steps, which equals bigger lander. No. No. I actually took the video to the office so they could hear it. I guess no one came, or they thought they'd fixed it. So this is going to be fast, longer steps, increase that. So that's going to be, which has the longer wavelength, it's going to be that guy. So there's two ways. You can do it mathematically. I can just say I get a fast speed by big steps. I get a slow speed by small steps. This one has the slowest speed, therefore must have the shorter steps. This one has the fastest speed, so must have the faster steps. So sometimes conceptual stuff gets it for you, and sometimes the other stuff gets it for you. I'm going to just plow through it because I want it on the recording as well. Let's get to good old Newton. Basically, put a whole bunch of put light through a prism, and the prism is a triangular-shaped piece of glass. And man, I'm having a tough time concentrating. It's right above their heads. How long we got before the end of class?
An hour.
We gotta go. We gotta go to another. I can't. I'm just take notes because I can stop this, but I can't record in the other room. I don't have the ability to record in the other room. So let's just stop.